everyone. My name is Georgia, and I'd like to welcome you to OP, home of the FRC Robotics team. Our first speaker is home of OP, the 2056 team, FRC 2056 team. Our first speakers of the day are Eric and Tyler, 2056, presenting 2056 ways to go.
Okay. So hello, I am Eric. Eric, I am the current lead software mentor, and I'm going to use it. You can use it. I'm the current lead software mentor, and when I was on the team, I was the lead programming student. I'm currently a software engineer at the University of Guelph.
I'm Tyler Boltzmann. I've been the lead design mentor for our team since 2007. My professional life, I'm a senior design engineer for Lakeside Custom Machinery. We make custom automations for the food industry predominantly. So it's kind of like FRC, except our game piece is like a bag of potatoes. 2010, I'm a Woody Flowers Award winner, and my university degree is actually in software engineering. Most people wouldn't guess based on what my kind of area of expertise is.
So today we're going to be going over the programming languages we use, a bit about how we plan our software, a bit about the software itself with subsystems multi-path programming. We're going to talk about driver controls, a bit about how we do vision, and we're also going to be talking about autonomous.
So, programming languages. You probably all know there are several programming languages that are available and supported in FRC. There's C++, Java, Python, LabVIEW. I think some other very, very obscure niche ones like ROS and a few others. But these are kind of the big three. And for the vast majority of teams, Java is going to be the answer. But we use C++ because, well, we always have. And our mentor base has lots of experience with C++, so that's what works for us. What works for you guys may be different, and that's totally cool. So every team's got to figure out, look at their own resources and their own goals when deciding, what language they want to use, whether it's Python or Java or C++ or, well, just don't use LabVIEW. Yeah, so programming languages in a nutshell.
So I don't know how many teams use version control, but we use it quite frequently. We use GitHub. And a big benefit of version control, which is when you can type your code and you can put it into a code base on the cloud, is you're able to collaborate with the team. A way that we end up using it is we come to a meeting, we talk about what we need to do, and we maybe assign that to students if it's not the beginning of the season, so they can maybe go off on their own and try to do it themselves, and then they can push it to the cloud as well. They can push it to Git and on a different branch, and that allows us to, once we meet together, we can review it, we can see what they did well and what might need to be changed. It also ensures that we have a stable version of code at all times, because you have like a main branch where your good code is, and you develop on other branches. So if for some reason, this is yet to happen, but it could happen, if they need to take the robot to like a sponsor event right away, and for some reason the code's broken, they can go to this main one that they know is going to work, they can bring it and they can deploy it, and it's going to work just fine.
So for me too, like I'll be at work on my lunch break, and I'll log into GitHub and I'll see there's a bunch of changes for some vision or something, and I'll have a read through it and go, oh, yeah, this is really good, we should pursue this, or maybe this is a different method of approach that we can pursue for whatever. We can provide some feedback, very quickly without me having to be here all the time, or mentors being having to be here all the time. Because Eric lives in Guelph. I do live local, but I've got a little 9-month-old at home, so I'm not here nearly as much as I used to be, or would like to be. So to be able to do review offline without having to be here in person is a big plus for us.
It's extremely beneficial. So one of the first things we do when planning is we make state machines.
Yeah, so we don't use the sort of command-based architecture that a lot of other teams use. We just have this very, very simplistic approach of what's called a finite state machine. And if you've never seen a finite state machine, it's basically a kind of flowchart way of representing different states that a thing can have. So a thing might be this hanger. So our hanger really only has two states, has up and has down. So if we were to draw this flowchart out, I can draw this out really, really quickly. And then I can show you how this is done. The hanger state machine is super simple. It has two states. Hanger up, hanger down. So within each of these states, in the hanger up state, we command the solenoid up. Come on in. We're short on chairs. Holy smokes. Come on in, have a seat. Yeah, George, if you can grab us some more chairs, please. Just kind of crowd around the back where you can, or fill in the cracks. So those of you who just got here, we very briefly introduced ourselves. My name is Tyler, this is Eric. We're software mentors for 2056. We use C++, other teams use Java, other teams use whatever, pick whatever works best for you. It doesn't really matter what language you use. There's really no competitive advantage to C++ over Java. It's really just whatever works best for you. So we don't use the command-based structure. We write our own finite state machines to control pretty much everything on the robot. And how this looks on the flowchart and how this looks in code are very simple. In the flowchart, there's two states. There's the hanger up state, where we put this solenoid on, and the hanger down state, we turn the solenoid off. The solenoid being the little electric valve that actuates this thing up and down. And the transitions between these two states are, there's only two of them. This is the hanger up button. This is the hanger down button. So on the joystick, there's two buttons that are mapped to these two things. So if you're in the hanger up state and the hanger up, the hanger is back. Apologies for my handwriting. It is there. So if you're in the hanger up state, you push the hanger down button, it goes to the hanger down state, and the solenoid turns off. Conversely, if you're in the hanger down state, you press the hanger up button, it turns the solenoid on, and the hanger goes on. This is a very, very, very simple finite state machine, just to show kind of how this works. Now,
On the next slide, we do have
this is an example from our intake. And the intake is much more complicated. So there were actually 8 states to it. The intake off state is, the intake's done. We have an intake on button that takes us to the intake on state. And in the intake on state, the motors are spinning as if we're intaking a note. And then once we stay in the intake on state until either the intake off button is pressed, or the intake reverse button is pressed, or there's a little sensor in the back of the intake, up about here, that detects when a note comes in. So when the note hits that sensor, this state machine automatically switches to this next condition, the intake hold state. And intake hold turns the motors back off again until the shooter is down in position and doesn't have a note in it. Oops, sorry. So you see there's shooter is less than threshold, so we're not going to transfer a note into the shooter when the shooter's up in the air. So if we were to pick up a note like this, the note just like stops right here until the shooter comes back down into position. And all that handling happens in the software. The driver has no control over that whatsoever. Now, how this looks in code is the easiest way to do it. Can you read that? The easiest way to do it is with a switch and a case. So in either Java or C++, the switch case function has different states. States can be just state 1, 2, 3, 4, 5, or we declare an enumerated type to give it a name that is something meaningful, like intake on, or intake off, or intake whatever. So we have a case, and within each case is actually what happens here. So it's the motors are running, or the motors are in velocity control mode, or the solenoid is spiked, or
see if we can actually take a look instead of just talking. Talking about the intake, right?
yeah. And the intake is a fairly complicated one, which is maybe not the best example.
Oh, but that's the one that we started talking about.
Fair enough.
Where's your intake holding here? Here. You can see here.
No, we can't.
Can you not? Oh, shh. How do we change this?
Is that better? That's terrible. Okay, so this is kind of what it looks like in code. So we have a switch with different cases, and then this is what we're doing in the state. So we're setting the intake motor to negative 75. This is velocity mode, so this is actually turns per second at the motor. We're turning these two motors on, spinning reverse, so we're spinning the node in. And the condition for leaving this state is we're not pressing the intake reverse button. So every time we're looping through this big switch case statement with all these different cases, and then there's stuff happening in the state, and then there's a transition to other states from each one. Can you go back to the very top? So we have a switch on our current state, which is what state the intake's on. And then from that flow chart, we have intake off, where some stuff happens, and then if the intake on button is pressed, we set the state to intake on, and then we jump to this state. So only one of these cases ever executes at a given time. And it's this kind of fairly simple approach to build complex functionality. And it gives you full flexibility to write whatever you want. You're not limited to some specific framework of, I can only make commands that are X, Y, Z, or whatever. You can basically write whatever you want. Like this condition for the transition might be, I've been in this state for more than half a second. Or it might be, the shooter sensor beam break is not made. So there's a little photo eye right here in the shooter that shoots across here to see whether we have a note in the shooter or not. So in the intake transfer state, we're running the intake until as soon as the shooter beam break is made, we switch the intake state to, well, this actually got quite complicated. We switched it to intake purge. An intake purge actually runs the intake backwards. This was not a great example because it is a good example because we had to do this really weird thing, which we could do fine because we structured it like this. When we would pick up a note, when the note made it into the shooter, we would actually run the intake backwards for, I think it was about a half a second. And that was so that if we picked up two notes, like right back to back, the two notes wouldn't get stuck in the robot. The second one would actually get spat back in. So that there were lots of times where you were picking up a note against the wall in the human player station. And there'd be kind of two notes there. And it was very easy to accidentally pick up two notes at the same time. So this code allowed us to pick up the one that we wanted, and then while we're driving away, the other one gets kind of spat back out the other end.
This is also a good example of how planning, you can plan as much as you want, but you can't necessarily plan for everything. It's very clear that this wasn't in our state machine that we showed you.
Yeah.
You gotta be flexible.
Can we go to the state diagram again? So this state diagram is just made in PowerPoint. And after we get the kind of mechanical architecture of the robot figured out, before we've actually built anything, we can sit down with the programming team and develop this flow chart and then write all of that code for the switch case before the robot even gets built. So that when it is ready to get powered on, we have code that's going to be not perfect, but it's going to be close. It's going to be reasonably close to the functionality that we're looking for, even for relatively complex things.
One point he didn't mention on this slide is we use switches obviously for subsystems like he's been talking about, but we also use it for our autonomous mode that we'll talk about later.
Yes.
Which loosely speaking, instead of having a state, it is more just like a counter that goes 1, 2, 3, 4, 5. It's just steps in an auto mode.
Yes. Yeah, your state diagram ends up just being a bunch of states with a bunch of arrows that go
Yeah.
straight down. Okay, that was a lot to throw at you at once. So are there questions? Yes.
Just curious about the set state.
So set state, all it does is it changes the current variable for the state to whatever it is that's in the parameter there.
It's very simple.
Yeah, it's just really an assignment of we're going to set the current state for the intake to the intake hold state, or the intake purge state, or the intake transfer state, or the intake reverse state.
Yeah, all the logic's done in the state itself, and then as soon as you call that set, it really is just set the state, set the variable.
So each state can have transitions out of it from within the state, or you can have kind of global transitions where if I'm in any state at all and this condition happens, I want to do this thing here. So in that case, we have some transitions that are outside of the state machine itself that just force it into these other states. So this manual on, manual reverse, those were manual conditions for debugging that we never used in competition, but they were there if you were goofing around with the robot here and you wanted to test functionality or something. So we didn't really use these, but they were there if we.
And in the past, we've used this before.
Yes.
This year we didn't have an operator, but in the past there's been scenarios where a robot might have broken, a sensor might have broken, and we've had to use these manual.
More questions? Yes.
Are there any disadvantages to just using functions over the switch case?
It's tough to build as complex a functionality with just functions, whereas a switch case you can do a lot more cool stuff. That's not to say that you can't do it, but I think it would be easier to implement it with a switch case. And lots of people will disagree with me. There are many ways to approach this kind of challenge. So this works for us. It may not work for you. Whatever works for you is what's best for you. More questions? More questions? Yes.
You guys explore compound checking with the state machine? Is like not going to wrong state.
No, that's not something we end up checking every compile time. We check with our eyes beforehand to make sure we think it works, but there's been a couple scenarios where you don't catch something in code and the robot does something we're not expecting.
You can definitely shoot yourself in the foot.
Yes.
So do you call the switch in a loop from periodic? Or like so does each subsystem kind of get its own branch and get called once and go through
Yes.
Each periodic?
Yes.
Yeah. So I can even show you.
Yeah, by all means.
So this is what our robot file looks like. Every first case, like auto init and auto periodic, as a subsystem controller that calls the subsystem's given thing, whether it's teleoperiodic or whatnot. So yeah, in that we have a subsystem controller, and in our subsystem controller we have an instance of all the subsystems. That all the teleoperiodic does is call a specific subsystem. So in this case, it calls drive base teleoperiodic and teleoperiodic. The drive base just calls the state machine. Oh yeah, it's so small. It just calls the state machine. Is that? Any other questions? I'm gonna have to go faster. We're already halfway.
Right. Multi-file program.
So you might have been able to tell from the code I just showed you, but we obviously use multi-file programming, and it works super well in object code like C++. And like I just kind of showed you, we have a file for each of our subsystems. And that obviously allows it allows it to be more readable. So if you have something wrong with the ARM, you can pretty well go to the ARM file and expect to find the issue there. It also allows for more modularity. We have an OPR calculations file that has a bunch of custom-made calculations that we can use throughout the code. And all we have to do is include that one file instead of recreating the function. It also allows for more collaboration, like I was talking about earlier with Git. If we maybe say to one of the students, you can work on this part of the code at home and we can review it after. They can work on their subsystem file, for example, and they can know that if we were to merge it in, or when we look at it, that there's no other changes to this file because they've been working on it. And it allows for merging of code to be a lot more simple. It also allows for better auto scalability. So our auto structure looks a little something like this. I don't know how you can see that. Okay. So in code, autonomous periodic is very same to teleoperiodic I just showed you. It's just calling the run. In this case, it's calling the run function of a different auto file. And all of our autos are based on a parent class, which has a bunch of commonly used variables throughout all the autos, but it also sets up the structure for being able to copy and paste autos, change something here or there, or even make very new ones. But there's this one parent file so that we know exactly what to expect when we're calling the auto mode in auto periodic. We also have an auto selector. So this is more before a match starts. Not really. But when the robot's disabled, when you're sitting there on the field before a match starts, the way we have auto selection from the driver is you hit a button on the controller and it's going to run that auto mode. We don't use smart dashboard or shuffleboard for any input. And this is because we've tried using it before and we've had experiences where it hasn't sent the data to the robot and we've done the wrong thing, run the wrong auto, or haven't gotten information even while testing, which can be annoying sometimes.
And if you're like scrambling before a match and you need to swap out your driver station laptop and you don't have the dashboard on it, you can still run your auto. You're not stuck because you don't have the auto chooser on your dash. You're still, you're going to be in the game. And it also makes sure that when the driver goes up there, you have to push the button. So we're sure that the joystick is actually connected to the laptop. It sort of serves as a double check because we've had matches before where you go up and the drivers go to operate the machine and nothing happens. And you're like, what's going on? Meanwhile, the USB is not connected, or there was static, or there was something that the drivers got jacked up with the driver station, and for whatever reason, the controller is not talking to the driver station. So by taking this approach, it verifies 100% that, yes, my joystick is plugged in, it is plugged into the right port, and the inputs are responding to the driver's command.
We also have LEDs on the robot that we use ahead of time to make sure that we've selected the right auto, but more specifically the right alliance color, because we have specific autos based on the color. It, I think, just inverts the points, but we need to make sure that we're running the right color.
Yeah, that's really embarrassing when your robot just like turns wrongly and drives into a wall. So don't do that. It's not inspirational. Questions? Yes.
So yeah, I guess you just touched on it a little bit there, but without like the smart dashboard, you're just clicking on a button. How do you actually get like the feedback from the robot that tells you I've selected the right auto?
So we don't have the elaborate dashboard, but you can still print to the terminal.
Okay.
You can print to the terminal. Now, don't spam the terminal with a billion prints. Print once on button press. And then you can verify that auto mode 8 is selected or whatever.
We also do have a box on the smart dashboard that tells you which auto you're in.
Yeah, but if your smart dash is not.
Oh, sorry, yeah, if the smart dashboard's not connected.
These slide order autos are in document files.
Yes.
I don't know that.
The very technical reason about C++, I couldn't tell you, but I do know that they don't need to be in C++ files.
But why is that not like an actual code file? Okay.
I honestly can't tell you. I'm sure someone made that decision a while ago, and it works. And like I said, I don't know.
We have another programmer mentor, Corey, who's not here, and that was kind of his baby. So, yeah, I don't.
So we're terrible.
More questions?
Yes.
How many auto modes do you have?
That many. Some of these are just like test modes, like the do nothing mode.
How do you have that many buttons on the controllers selected?
So only 12 of them are selectable. Some of them are they're there and they exist in code, but they're not even selectable.
But 12 buttons on the controllers are dedicated to auto modes?
While the robot is disabled.
Yeah.
Only while the robot is disabled.
Yes.
So going back to the state, can you do state machine in command-based programming, or is that making two very different frameworks?
We haven't really used command-based all that much. We might have before my time, but as long as I've been here, it's similar to how we use C++. We kind of use time, and it works for us. So you might be able to, I'm not sure.
More questions? Yes.
Do you guys simulate stuff?
I read the code and I think about it. That's about the extent of our simulation. Yes. I'm glad you asked that.
Let's go to the very end.
Okay, we're gonna blast through the rest of this.
The rest is kind of-
Control loops. So the act of making something do something that you want. Like if I want to drive this arm to this position, we're big fans of the cross the road motion control software. We use pretty much exclusively the cross the road controllers because their built-in motion magic and velocity control and positional control is way better than anything that we're going to write ourselves. So we just use their stuff. We use their built-in libraries for motion control, and it's easy to implement, and it just works. It's quite a bit better than the comparable Rev one. I don't know what they call Smart Motion or something, but yeah, the CTRE stuff is really, really good. So we stick basically exclusively to their control loops for well, pretty much everything. Like the shooter was velocity control, all the conveyors were velocity control. The arm was motion magic if we were doing a really big move. And if we were doing a small move where we're just tracking the goal, we would use positional control. Because positional control follows a moving set point better than motion magic does. But motion magic is really good at long moves where you want to have a control velocity profile where you accelerate, go fast for a bit, and then decelerate. So motion magic is great for that. Questions on that? CTRE Pro. So Cross the Road has this pro version of their software that's $150 a year that you pay for a subscription. And there's been a lot of controversy over this because people think you should get software for free. Yes, it's $150, but CTRE has some very, very smart people that put an awful lot of work into developing and maintaining this software. And the only avenue they have to recoup that revenue is selling you this amazing motor that you can reuse year after year after year. So it is a terrible business model for making money. So they have this small subscription fee that gets you the swerve drive generator, the field-oriented control for the motors, which gives you very, very slightly better motor performance with a Kraken or a Falcon. Gives you this fused CAN coder functionality, which allows you to hook up an external sensor, which is really just the steering for your swerve. If you do this, it's way better. And the time sync. The time sync, I'm going to gloss over this quickly, but the time sync, when you ask for the position and velocity of all of your different wheels, it makes sure that all of them are synced up to within a millisecond or two of each other, so that when you calculate how much your robot moved from one cycle to the next, everything is time synced. And if you don't do that, you can have a fair bit of latency from wheel to wheel to wheel, which makes your calculation of how much I moved every single step less accurate. So they have this functionality that allows you to, in one line, synchronize all of these sensors and get the values from them in one shot. That just makes odometry much, much more. So for us, the $150 a year is a no-brainer. We're going to pay this at the time. We're not sponsored. It's just good functionality that is worth the whatever $150 a year is. Moving. Robot control. So we have one. Is this your spot?
No.
We have one driver.
Hours, they're all hours. Right?
We generally try to have one driver control the entire robot. And the reason behind that is if Eric and I are driving this robot and I go, hey, Eric, move the arm up. Oh, okay, sure. And then he moves the arm up. Or I can just push a button and the arm goes up. So verbal communication is very slow. And it takes a long, long time for two people to practice driving a robot together to the point that they basically function as one. So we just don't have two people. We just have one person drive the whole thing, or as much as one person can reasonably have. And then we'll offload, maybe there's some end game functionality or something that the operator will do, or the operator basically serves as a second coach, and the driver is controlling as much of the robot functionality as possible.
Last year's a better example for this, for having two drivers, because last year we had two drivers, who was mostly a drive code.
Yes.
I believe he'd call out where to place pieces.
Yeah.
And he was responsible for signaling to our human player what piece he
Yes.
wanted, as well as manual controls that we were talking about earlier. They'll have the responsibility for that.
Yeah. This year the robot was entirely one driver because we didn't really have all that much functionality that we needed to have to. So we're generally always going to have one driver if at all possible. And if you have so much complexity that you need two drivers, you're probably doing something wrong in the first place by building a robot that's too complex. Questions on controls?
You can see the control mapping just quickly here. Everything you want to do is on this control.
Yes. Left stick is robot translation. Right stick is robot rotation. If you click right stick, we never do this, but if you click right stick, it switches to robot-centric driving. If you click left stick, it switches to field-centric driving. And basically, we just always field-centric drive.
Something I think we forgot to mention is half the way that we can have one driver is with the driver assists.
Yes.
Like last year, for example, or I guess this year, for example, we had a lot of driver assists for shooting, for picking up, for scoring in the amp. Everything had some part of it that was automatically done to make driving it alone significantly easier than if you didn't have these assists. And we touch on that a bit more right here. So
just if we can back up for a second. It was left stick translate, right stick rotate, and then the triggers were intake off, intake on, right trigger was shoot, and then right bumper was intake reverse, which would just like purge the intake back out. And then on the kind of letter buttons, flywheel spin up. This home position would just put the arm down and turn the shooter off. Overhead shot was super cool. Overhead shot would flip the shooter up like this so that if there was like a tall defender in front of us, we could shoot over the back of them. But if you held the button down, it would snap the robot to a specific heading so that if you stuck the corner of the bumper against the, what's it called, the podium?
I think so.
It would be lined up with the goal. So the driver would just hold that button, the arm would go up, spin up the shooter, the chassis would snap to the right orientation, and then he would just put the corner of the bumper against the thing, and we knew the shot was going to go. So we didn't have to like manually try to line the robot up because the aiming camera was actually the other side of the robot looking the wrong way down the field.
Yeah, he's so good at the practice.
Yeah.
And then just on the back, we have the controls for the hanger.
Yeah. That's super cool too.
Yeah.
We use this Fusion,
Xbox Power A Fusion Pro controller.
and it's got 4 buttons on the back. Now these aren't really extra buttons, but you can map these buttons to like the D-pad, which you're probably not going to use anyways, and then use the functionality off of that. So basically it kind of doesn't gain you 4 buttons, but it gains you 4 buttons.
And most of the time, the driver's not going to take his finger off the drive stick, so the D-pad will be mostly used, at least the way our drivers.
And when we're sort of choosing the button mapping, we're choosing functionality on here where the driver doesn't need to aim. Because like when your thumb comes off the aiming stick to do something, and you can't steer your robot. So if we have functionality that we still need to be steering the robot with, we put those on the back, so that the thumb never has to come off the thumbstick
Or the triggers and motors.
or the triggers and motors.
Something we loosely also try to do is group controls. Like most of the face buttons control what the arm is doing, and most of the bumpers are controlling what the intake is doing. Aren't always able to do this, but you loosely try to have the same thing, the same subsystems on the same type of buttons.
And right trigger should always be shoot, no matter what you're doing.
Absolutely.
Kids play video games, so make it as close to video games as you can.
Any questions?
Yes.
For all of your position buttons, like, is it just spinning up the shooter and putting in position, and then you have to press the shoot button itself to eject?
Yeah, you actually have to press the shoot button to send it. And the reason we do that, rather than just like letting the robot shoot when it thinks that it's going to go in, is like you might have somebody coming downfield about to clock you. So you don't want the robot to be like, "Yep, I'm good to shoot," and then get smoked. You want the driver to have a dedicated thing where, yes, I want to in fact shoot the games.
Also have to remember vision isn't perfect. So if you rely on vision saying that you're lined up, it could be pointing over there or over there. And all of a sudden it thinks it's lined up to something that isn't actually a target and would send it off to the current, which is not good.
Okay, what? Yes, we do. When we pick up a game piece, we give it like a half-second vibrate, because sometimes you can be at the far side of the field and you can't see the robot or whatever, so we rumble the joystick for a half-second when we pick up a game piece. Yes,
Do you have anything indicating when the robot thinks it's ready to tell the driver press the shoot button?
the whole robot turns red.
The LEDs on the robot will turn red.
When we can see a target and the shooter is spun up, but we're not lined up, or maybe the shooter, we have some condition that the robot doesn't think that it can shoot. They go one color, and then when it's ready to shoot, they switch to red.
Okay, quickly talking about vision. We had a lot of questions this year from teams talking about the 3D pose, because we use a limelight. Actually, we use 2 limelights on our robot this year for cable tag tracking and AP tracking. And I think a lot of teams maybe not use the 3D pose to know where they are on the field and to line up with the target. And we don't do that for anything this year. We experimented with it, but we found it was unreliable the way we wanted it and the way we had the camera set up this year. So we have one limelight 3D for cable tag tracking, and we found that is extremely reliable. And all it does is it lines the center of the robot with the center of the target, and the driver knows that he has to be in front of the target to actually hit it, because when you're not lined up with the target and you're completely skewed and you think you're lined up with the airport tag, sometimes you shoot past or you shoot it into the corner of the speaker.
Yeah, basically the limelight, you can set it up in like very simple 2D tracking mode where it just tells you where the April tag is in your field of view. So it's 5 degrees off to the right and 3 degrees up from center. And it'll do that at 60, 70 frames a second. It'll do that smoking fast. If you set it up in the like 3D bot pose tracking mode, it'll give you like your XY position on the field relative to, I think, that corner. But it only runs at like 20 frames a second or something. So it's not really fast enough to use as a real-time sensor for the purposes of aiming your robot at that goal when there's a robot smashing into you. So we take this very simplistic approach to approximating our angle and distance from that tag and that tag only. We don't even look at the rest of them for the purposes of aiming. I mean, we don't do any kind of 3D localization of figuring out where the robot is in the field, because really all we care about is that we're pointed at the goal and then the shooter is on the right angle. The rest of it we don't really care about.
We also vision track the targets, and instead of doing AI tracking, we do kind of like the retroreflective tracking. We look for a big blob of orange on the field, as you can kind of see in that picture, and it's the same thing as the April tag. It gives you an angle offset from the center of the camera. So you just in our case, we translate until the center of the robot is centered with the game piece, and then the driver drives forward and picks it up.
Yeah, the machine learning, you can plug in a Google Coral machine learning accelerator, and you can give it 50,000 images of what a note looks like, and it'll do more or less the same thing, probably better, but slower. So when you're just doing simple color tracking, it'll run at 95 frames a second, and then you can just treat the camera like a real-time sensor and directly close loop control on whatever the sort of position of the note is in the field of view. And we can drive full speed downfield, holding the intake button, and the robot will see a note 3 feet off to the right and zoom way over without the driver having to give any input whatsoever. It's super cool to see it work.
That's another thing.
It just looks for an orange block.
Yeah.
We're not doing anything fancy. But this approach is susceptible to lighting. Yeah, and really worn notes. They lose the orange skin on the outside, so it struggles with really warm notes or venues with really poor lighting.
The April Dex also says that.
Questions?
So do you just have how does the controller work for setting on that? Is it just a PIE controller from angle of the sensor to the translate?
Is this it?
I think that's it. Pretty sure it's. I don't know.
So we take the camera's horizontal offset, which is the X offset in the field of view of the camera. We multiply that by however fast the robot is going currently. And then we have this kind of cheesy variable that we pass into the field center controller. And what it does is the robot coordinate system's like this: positive X, positive Y, positive Z. So if we see the node over there, we know that our horizontal offset is whatever, 10 degrees. We add in some robot-centric Y velocity corresponding with how far it is off our field of view and multiply it by the current speed of the robot. And then there's this constant, which is just some arbitrary number that we tuned a little bit until it responded the way we wanted it to. But we scale it by how fast the robot is going. So if you're going really slowly and I see a note way over there, I don't want the robot to just zoom over to the side. We kind of scale it by how fast the robot is going right now so that it will kind of slowly move over, but it won't just take off and zoom. So stuff like this, it's just really simple one line of code that makes a massive difference in robot performance.
Yeah, even in the field sensing drive, I think it's another line of code.
It just passes it through to the robot center.
That's it.
More questions? Yes.
You use both the robot and
Oh, we just look at that. We don't look at the other one at all.
Anyone else?
Yes.
I'm assuming then you just use the one that it's not there.
Well, we don't even look at it at all. So the amp one, when we hold the amp button, it puts the arm up to the position and it just snaps the robot to 90 degrees. And then the driver drives it in and lines it up and then sends it. We actually can't even see the amp effect of our cameras.
Is your dollar to the after or position by?
Well, the gyro. The Pigeon from CTRE is unbelievably accurate and consistent. Yeah, it's really good. Over 2 minutes, you don't really lose any accuracy. And that's the one sensor that you can truly trust no matter where you're on the field that 0 degrees is downhill or downfield.
That's another thing I didn't touch on when we talked about traffic controls. We did at one point try tracking with the April tag, even though we couldn't see it right up close. You could see it from maybe a foot away. So we tried looking at the April tag and doing the same kind of translational thing or even a rotation thing to try to help the driver. But every time we did it and we added it, we couldn't get it working in a way that he liked. And it was just better for him if we didn't have it. At some point, you can't force your driver to use your code. If it doesn't help them, don't let them use it.
Yeah, if it's no better than what they can do themselves, then you're better off to just let them do the thing. Oh, this is the worst thing ever. So I mentioned we just look at the one tag. So figuring out this is really easy. It's just the number that comes straight from the limelight. Figuring out my distance this way is much more difficult. So what we do is we use this interpolating tree map, and that's built-in functionality in WPI Lib, where you map one value to another. So we park the robot on the field here at a known distance away from the goal. We measure what the TY value is in our field of view and the actual measured distance from the wall, and we plug this into this table. So we take measurements at 6-inch increments all the way back, looking at what the TY value is from the limelight to the actual measured distance on the field. And then no matter where we are, if we're pointed at the goal, we can figure out what our distance away from the goal is just with this lookup table. So when you get a value from one of these interpolating tree maps, if you're in between these values, it linearly interpolates between the points. Okay.
There's some.
Yes.
It's very good, but you have to do this at like every talk because it's
Yes.
lighting.
So it's not the difference in lighting, it's the difference in the field. If that April tag is a 1/4 of an inch higher, that makes a significant difference, especially when you're back here, a little bit of difference there makes a big difference in the field of view. And that April tag might be 1/8 of an inch higher than that April tag. So we have a map for the red side, we have a map for the blue side, and we recalibrate that on every field. And like there might be a divot in the floor here because there's a drain. And then at that specific range, your robot tips back 1/4 of a degree, and that throws your distance off by 6 inches, and now your shots all go high. So by doing this, we take all of those variables into account so that we don't care if this camera is different than the camera on the practice robot. It takes into account camera mounting, field, red, blue differences, all of those things to make sure we have an accurate distance. Yes.
How long does this take?
About 15 minutes if you get really good.
How much time?
Yes.
Usually from this speaker wall to the bumper or like this middle of the box.
However you choose to define it, doesn't really matter as long as you're consistent with it. We measured to the front bumper because it was easy to do with the tape. So we have a similar interpolating tree map that goes from linear distance to shooter angle. And the way we figured that out was we parked the robot on the field, eyeballed the shooter where we liked it, and then put that into the table and then move back. Put that into the table, move back, put that into the table. So that we go limelight to distance, distance to arm angle. And then the distance to arm angle one never changed all year. But the TY to distance, that did at every single event. Even sometimes over the course of an event, because the speaker wall will get smashed and then move back 3 feet and then everything goes forever. Okay. So lots of teams have complimented us on our auto modes over the year. We have a very kind of incremental approach, and we devote a lot of time to developing auto modes. My other presentation later today, I'll talk about our schedule, but we basically devote 6 weeks to developing auto modes. Huge amount of time to just auto mode development. And we start very small, and we build incrementally more and more complicated auto modes. But almost all of them rely on having all of the automation in place on the robot for note handling and auto aligning and auto aiming and all that fun stuff. And once you have that all in place, you can build auto modes fairly quickly. But we generally have very incremental testing where we start with something very simple and then you build and build and build.
And this is probably a really small example of what an auto mode looks like.
The slides will be online later. It'll be easier to read. But basically, it's the same kind of switch cases we had in the state machines, except the cases just go 1, 2, 3, 4, 5, and those are basically the steps of things that we're doing in auto mode. So our first auto mode might be we're going to spin the shooter up, we're going to auto aim, and we're going to drive to some point like 6 feet behind us. And the condition to move on to the next state might be the shooter is spun up, and I have a valid target, and my valid target is less than, basically I'm pointing at the goal. And that's the condition to move on to the next state. And the next state will be, I'm going to turn my shooter feed rollers on until this photo eye turns on. And then I move on to the next state, which might be to drive to a game piece way out here.
freeloaders.
So the structure is very simple. There's really nothing, elaborate to it. But you can see an example here is drive base, drive point. We're driving to this point that's called node 2. Node 2 is a point in space that has an x, y, and an orientation. XY coordinate and orientation. We're driving there with speed, which is some variable that we set previously, probably 190 inches a second. And I forget what this parameter is. Oh yeah. How fast we allow the robot to rotate. So we do some stuff, and then when the shooter beam brake is off, we set the robot speed to something else, and then we move on to the next step. Yes.
All right, so note 2, you said XY rotation. Is that the rotation of the robot's heading?
Yes.
That it's driving to? And then what's the next? What's the head after that?
I don't remember.
Threshold.
Oh, so that's how close the robot has to be to node 2 for this condition to evaluate to true. Because sometimes we use this as the condition to move on to the next state. So we give it an allowable tolerance around the point that if I'm within 10 inches of where I'm supposed to be, this statement is going to return true.
And how do you handle if you want to maintain speed between two sections of the other? If you want to keep your speed as good.
So there's an optional parameter that's not shown here that's we call continuous. And when that parameter is true, we don't look at the distance away from the point. We just go whatever the commanded speed is towards the point.
And then you also just wait till you're within your tolerance.
And then move on to the next
What
point.
if you drive past?
Then you drive backwards towards the point full speed, so don't do that. It is, yes, it is exactly what it is. But you can string a series of points together and just go blazing around them. And it's super easy and simple. Yes,
How do you deal with getting hit?
we have bumpers.
No, like, how does if the robot gets hit, right?
Yeah.
You guys don't have localization, so how does it correct for it?
We don't.
Oh.
So when we come back and shoot, when the robot is stationary, we can calculate where the robot is in the field relative to that April tag. When the robot is stationary very easily. So every time we come back and shoot, we relocalize. But the drive moves in between, we don't. Yes.
It's wondering for slide 4. So we say you use typically map to map your the field at partition to, are you mapping to this field basically, or are you mapping it to like what is the dimensions you're mapping?
We're mapping the distance from the wall to the robot's April tag position. And we do that on each field.
Okay, but like what positions, like when you map like the position from the speaker here, like so like you get the distance from the robot to that April tag,
Yep.
and then if you go to your field, do you like basically just map like one like stored location to another stored location, or like when you have like when you have your distance, like where is the distance coming from? That's what I was gonna say.
Like we measured it empirically on the field.
Oh,
We plunk the robot down during calibration and go at 36 inches, this is our TY value.
okay.
And at
With the
42
measure.
inches. And like literally with a tape measure, move the robot 6-inch increments,
Okay.
measure that. And we do that on every field.
Okay, no, sorry, I think maybe I'm asking the wrong thing. How do you get, so the TY and the X, right? You have those, like, where do you get those from? Before you have them?
Oh, they just come right from the limelight.
Okay,
Yeah, we just buy the limelight, set it up to look for April tag number 7.
Okay.
And those are just raw values we read in.
okay.
Question with the drive to point.
Yes.
Do you just have like a separate like X and Y PID controllers on the drivetrain, or how do you actually go from where you are?
So I'm here, I want to get to there. Calculating the distance to the point is like
Yeah.
grade 10 trig.
Yeah.
So we have one for the distance from the point that controls the velocity controller. We take the XY difference, feed that into the field centric controller, and then there's another PID controller for the heading. That all feeds back into the same field centric drive controller that we use in teleop driving.
So you always just basically drive a straight line to the point with one like distance PID controller.
Yeah.
Really quickly, because we have like a minute, but this is like the last slide.
Logging. So yeah, we don't do any logging.
Yeah, so we don't do traditional logging. Like during the match, we're not logging numbers to a file to look at later. But what we do is record the driver station screen with OBS during a match. And you can see that here. So you can see here all of the numbers that we could probably need to debug what went wrong in a match. They're going to be somewhere on this screen. The benefits to doing this is we also have cameras, as you can see. You can see what the robot was doing. We can see what the robot was doing when the thing happened, and it also allows us to, I guess.
It also records the laptop mic, so you can hear what all the drive teams are saying in a match and analyze the communication that goes on there. And that's a big thing too, separate from code, is just analyzing that communication to make sure that you're working effectively. So this takes us 5 minutes to set up and 0 time whatsoever to maintain across the entire system. And it accomplishes all the goals that we need.
Yes, and there's also just like to keep things out of the code base that don't need to be there, like there's no extra code for logging.
How many points do you get for logging your sensors? 0. So we don't put any time into it. There's a question over here.
It's like nice to, like you said, like if we add something to the dashboard, we don't have to think to add logging for it. It's just there now. Okay. That is the end. A sponsor's language, I guess.
Thank you to all of our wonderful sponsors. More time for questions. Do we have time for questions? Or
We have 10, it's 10. It's 10.
It is exactly time.
Exactly.
Okay, thank you. You've been a wonderful audience. If you have more questions, just grab me at any point throughout the day.